Hello everyone, my name is David Perea Santos. I'm a student of the PhD program in the Center of Research in Applied Science of Advanced Technology. And now, in this occasion, I want to present the poster. The name is High Ion Conductivity at Room Temperature in a Family of Composite Membranes, Divalent Transition Metal, Hexacenocobaltates, Polyterimide. As introduction, proton conductivity behavior was studied in a family of hexacenocobaltates with divalent transition metals and mixed matrix membranes. The hexacenocobaltates had cubic crystal structure. The porous materials and the composite membranes were characterized and electrochemical impedance spectroscopy tests. Electrochemical experiments indicated that the materials have great conductivity, values 10 raised to the minus 4 and 10 raised to the minus 2 Siemens centimeters for possible application as proton exchange membrane. Following the purpose methodology, first, we began with the synthesis of the hexacenocobaltates, subsequently the preparation of the composite membranes by casting and characterization the powders and the membranes. As we can see, the first characterization is ER spectroscopy. We can see the characteristic bands of hexacenocobaltates from 2100 to 2400 centimeters. As well, the thermal analysis of the materials, we can see three losses mainly of superficial and interstitial water molecules, as well as loss of the solvent being stable above 300 degrees and likewise degrading at 400 degrees. Through impedance spectroscopy, we can observe the different diagrams such as Nyquist, where we can see the capacitive and resistive character of the materials and the characteristic spike of the diffusion of ions in the lattice. Through tangent delta, we can determine the maximum frequency in the both diagram to see the coincidence of the conductivity. And likewise, through same micrographs, we observe the membrane composed of the hexacenocobaltates, where we can see a homogeneous and distributed phase with grains to 1 to 2 micrometers and agglomerates of up to 3 or 4 micrometers. In the other side, through this diagram, we can observe a schematization of how the implementation of this type of solid electrolyte will be in a fused cell, where we see the anode that decomposes the hydrogen and the electrons travel in an external circuit and the protons travel through the solid electrolyte, allowing its conductivity where it reaches the cathode. The results obtained, the membranes, the proton conductivity values obtained at 99% humidity relative and room temperature for P conductivities of 10 release minus 4 were obtained in the range of 10 release minus 2 to 10 release minus 3 with hexacenocobaltates of cobalt, manganese, zinc being above iron, copper, and nickel, where values 10 release minus 4 Siemens centimeters were obtained. As you can see, the diagram represents the different conductivities of the membranes. Comparing the radial scheme compared to the powders, the conductivities are very similar. And now, given the polymeric matrix, they now have a structure for the powders. how to conclude the conclusions from the standard chemical precipitation method. Transition metal hexacyanocobalt were obtained in the form of powders as well as mixed matrix membranes. By the casting method, each powder and membrane of the family was characterized by ER, TGA, X-ray diffraction, and spectroscopy electrochemical. The characteristic phase of the hexacyanocobalt was obtained and a good incorporation into the polymeric matrix was obtained. According to the evaluation of the powders of spectroscopy impedance, good conductivities were obtained in the range of 10 raised minus 2 Siemens. The highest began copper, and according to the membranes in the range 10 release minus 3 Siemens were cobalt, copper, being excellent conductivities at room temperature. And that's it. Thank you for your attention, and see you in the next program.